So they asked me to give an opening set of comments to try to set the stage, which is a very daunting task, because this is not an immediately apparent subject for many people, but I think it's one of the most important trends going on in technology right now. In fact, last year at a Churchill Club event, when we were charged, a whole group of us venture capitalists, to come up with what we thought were the most important tech trends for the next 3 to 5 years, I highlighted machine learning in general, which encompasses, in many vernaculars, this whole concept of deep learning, as well as traditional classifiers and such, as the single most important technology trend, one that's really underappreciated, but really seems to underlie almost everything exciting that's going on, let's say at a company called Google. If you look at anything, it's a way to make sense of what Google's doing, from autonomous cars, just about everything except Loon fits in the framework of using machine learning and deep learning techniques to make sense of big data in new markets where competition hasn't been seen for quite some time. And this is true also for a number of the startups that we invest in. And so, in a way, what I'm going to try to share with you is what is this common pattern that is striping across so many different domains, not just the deep learning area, but more generally this idea of how we use computers to transcend human limits, to build artifacts and solutions to problems that exceed human understanding. And that is a breathless undertaking, right, to be able to do such a thing. And hopefully through this perceptual prism, you'll be able to see both patterns in, what's going on between some of the giants of the Googles and Baidus and Facebooks, why they're gobbling up companies at such an early stage, and why they might acquire companies in such diverse areas to get the talent, right, the people that know how to solve these kinds of problems that are on this form of the sort of engineering of the future. So, with that, let me just share a couple thoughts about machine learning. Oh, I thought I had this up here as I was speaking. So, deep thoughts, I added a little smiley face because I had the struggle to have some deep thoughts to share with you today, and I certainly will fail on that, but I will try to share at least why I'm enthusiastic about today's panel. Let's see if it goes forward more. Okay. So deep learning, just one slide, and you're going to hear an example from our first speaker that kicks off the panel on what it's good for. So for those who just aren't aware, and I'm going to try to keep this at a very lay person level, hence Jennifer Aniston, image recognition is far and away one of the most widely reported on and sort of tangible areas where progress is being made of late. Obviously, speech recognition, textual recognition, and the translation that goes into grammars are all areas that also relate to this. It's basically areas right at that cusp of what we might expect computers to be able to do if they were intelligent, right? This definition of AI keeps slipping out. Maybe we thought Siri was cool for a month or so, and we want something more. And what I might say is any product as a consumer that excites you over the next 5 years and makes you think that was magical, how did they do that? It's probably based on this. Whether it's autonomous cars or what have you, at least for a key part of the underpinnings. There's also stuff that goes on into how hedge funds can make a ton of money, and then on the useful side of the spectrum, how we can do a better job than most doctors do in diagnosing disease. It's absolutely the case that we'll look back at the present day and marvel that we had 2 or 3 variables in a human brain to try to make this complex pattern match of symptoms to disease, or from genetics to likelihood of disease. We've invested in one, Human Longevity Inc., that's just trying to take on that simple task of extending our lifespan and to use these methodologies to say, forget most of the bolus of the current medical approach. Let's just look at all the data and see what we can learn. And they just pulled Franz Ock out at Google to lead that effort. He formerly spent 10 years doing the translation projects and other machine learning projects at Google. So those are some of the areas, but there's many more, right? Obviously, the big acquisition of the British company DeepMind and others by Google show that there's quite a bit of excitement in this area. Now, since we're at Stanford, I thought I'd do a little bit of a wayback machine, for me at least. Literally behind my chair at work is this book on the left. It was a course I took in 1987 by Professor Rummelhart. It was in the psychology department, and it was on this thing called neural networks. And as you'll notice, this one actually gets into the psychology and biological models of that. I don't believe there were any other engineering students in the class, and there were only a handful of those who would be considered computer scientists in the present vernacular. By the way, if you fast forward to the present day at Stanford, you want to guess what the single most popular course at Stanford is? CS 229, machine learning. 750 students last year. Now, to be fair, CS 106A has more because they have multiple sections across quarters, but the single most popular class is a graduate class that requires you to know linear algebra, computer science, and probability theory. Has some serious requirements for a graduate level course, yet 750 students find it very popular. Generally speaking, when you talk about neural networks, and this would be the stuff we studied in the 80s, they'd look kind of like this simple thing. You have some input variables, you have some hidden variables, and some output variables. You pass, let's say, some form of input, the pixel map from a camera, let's say, and let you try to recognize the letter A, B, C, or D. You basically just present iteration after iteration of examples and backpropagate errors through this. What you're basically doing is adjusting the weights between these nodes. Each node, loosely patterned after a neuron, has a little sigmoid function or a nonlinear transfer function of some sort that basically, in a sense, mimics at a very high level abstraction what a neuron might do. It says, when do I fire? Well, when there's a certain number of my inputs are activated, either positive or negative. And then what you do is you just use the same network or something like it to brute force figure out solutions to problems. Now, there were a lot of interesting implications of this back in the day. Like, you didn't understand very much about what each of these nodes or weights meant. All you know is that it did a good job. And in the early days, it was speech recognition. And Kurzweil and others would start to predict that this would eventually percolate into vision and other more complicated tasks, as it has. So now, fast forward to today. Some of the most recent work last year and leading up to it before that by Google was this Google Brain project. And we have a representative on the panel who we can hear from directly later. But lo and behold, there are cats on the internet. This was, of course, the most profound discovery at some level that without any prior filters or tilting to say, let's look for this, they just presented 10 million video clips, actually very short, single frames from 10 million videos, and just said, what do you find, using a new kind of deep learning methodology, which I'll explain in a moment. And lo and behold, out like the ghost in the machine come cats on the internet. That's because there are a lot of cats on the internet, actually, and a lot of them in YouTube videos. But there literally is like a node, if you imagine like a neuron equivalent in the brain, a little node, like that's the cat thing. It after a lot of training, realized there's a common theme. All the different orientations of cats, that thing lights up when there's a cat. And by loose analogy, that people have found the Bill Clinton neuron in certain brains under neurosurgery that literally they light up this little region when you think about Bill Clinton. Can't think of why that's particularly relevant, but it seems somewhat, oh, interesting, this is cropped off. Oh, cool. Well, this would be interesting to see what happens. I just realized my slides are cropped off. Okay, cool. So what do these all have in common? They're iterative algorithms. Much like evolution itself, you get to a solution by iterating on a very simple to describe. It may have sounded a little complex the way I said it, but if you actually draw it out on paper, it is one of the most simple ways to think about solving a problem. It's very generic, very fungible, much like evolution itself. It can do a lot of amazing things, and it can lead to complex artifacts that transcend the complexity of their antecedents, which is why it's powerful. The thing about deep learning, though, that's different from some of the neural networks that we saw in the 80s that I was referring to in my first exposure is that you can have learning now at sort of multiple layers of abstraction. You think about, like, let's say in the vision system. So low-level neurons might be edge detectors. Higher-level neurons are, detecting cats. And those sort of multiple hierarchies of layers and the ability to do successive training from a bottom level to higher is some of the big breakthroughs that Hinton and others have discovered methodology. So there have been some advances. But in general, across all these, you have some nonlinear transforms, that sort of sigmoid function, and a lot of steps in training these things. I'll get some other generalizations in a moment. Now, what's new? Like, why isn't this just like neural networks all over again? And many people I speak to in this field will say, well, yeah, those books in the 80s, they really had all we needed to know. But there have been a few meaningful advances. Why? Sort of the why now question for perhaps your enthusiasm for being here. The first is we have a lot of big data. I mean, there's just a lot of data. And you hear the word big data thrown around a lot, which frankly would just mean big problem if it weren't for machine learning and deep learning, right? I think it's kind of a misnomer when people say I'm excited about big data. There's nothing really exciting about it until you have a methodology to make use of it, because we can't understand big data. I mean, none of us wants to read through a phone book and try to make sense of it, right? So the data only makes sense because of these technologies. And where does it come from? Of course, the internet gives you access to a lot of stuff. You have also a lot of metadata, people that are voluntarily tagging photos or what have you, and a lot of documents, like the English and, let's say, French version of a document that allows you to perhaps to do automated translation. It's just the scientists love the data, and there's a lot of it. And you also have Mechanical Turk. In a lot of research projects, people can just farm out tagging to double check if their system works by just paying ridiculously low sums of money to have humans label things and they compare it to their artificially derived deep learning network. So big data is one of them. The other is algorithmic advances. And I won't go through this as much. I might leave it for the panel. But first, some of the advances that make deep learning more interesting than the 80s version of neural networks is that now people have figured out a variety of ways to work on unlabeled data. So back in that Google experiment, none of those videos were labeled cat. And they didn't look at that, right? They just looked at random images from videos. And catness came out of it, if you will, right? That's powerful, right? Because there are only so many labels. There's much more data that's unlabeled than labeled. What some folks have figured out how to do is to use this sort of unsupervised methodology, this sort of just expose stuff to the network and figure out a topology, right? Have it, there's a sing-along. I think there's a messianic sing-along. Okay, embarrassment's over. that can get you a structure, something like the features or edge detection, basic structure of what you have there. And then they can use this traditional backpropagation where you propagate errors back through your weightings to actually classify what you've labeled and figure out, well, that's the cat neuron. And basically, in a simple line, perhaps you could say, you have successive layers of learning that can make this deep, hence the word deep learning. Okay, enough about that. But here's what I think is kind of interesting. It's basically, we can do a lot more now. I mean, if nothing else, some people would say, take neural networks, apply them with today's computers, you'd see a lot of the advances. Because back in the day, you might have had a neural net that had 1 to 10 million, in a sense, synapse equivalents, like if you think about the synapse or the connection between neurons in a brain, or the fan out between nodes in aggregate. When the Google Brain Project first announced the cat result, they had an aggregate of 1 billion. And this, of course, is thanks to Moore's law. In fact, one of the things they had, of course, is 10 million videos to look at. Just the mere fact that you have digital access to such a thing helps, right, being Google. And having 16,000 computers to run for 3 days on the task also helps if you're Google. And we'll get to that later, how much does it help to be Google in this whole field versus just about anyone else. But here's another comparison, lest we get too far ahead of ourselves. There's still a long way to go, right? 1 billion synapses in Google Brain is a far cry from the 100 trillion you have. Everyone here looks like they're older than 3 years old. Yes, the 100 trillion synapses that you have in an adult brain. But when you were born, you had a quadrillion, right? You had 10x as many synapses as you do now. With a massive pruning exercise, it was cut back. It's also kind of interesting when you look to nature that the number of synapses per neuron grows as a power law with brain mass. And I'll explain what that means. So Jeffrey West at Santa Fe Institute looks at various power laws in biology. Why is it that our perfusion system is the way it is, and the number of heartbeats, for a mouse is about the same as a whale across this huge dimension of scale of mammals from smallest to largest, such that we all have the same number of heartbeats across all the mammals, which is kind of a weird corollary. But back on topic, one of the weird things is that as brains became larger, the fan out just goes up as a power law. And there isn't a causality arrow in that one, unfortunately, that he figured out. I wish he had. But it sort of hints that this might be necessary to get human scale intelligence. And that might speak for different topologies for how we build hardware to do these kinds of things that may look more like our brain, right? Where we have 60 billion neurons. It's about 100 hertz processing rate, really slow, but massive fan out and massive synaptic connectivity. Now, Moore's law, Google, lots of computers. How many people have seen Ray Kurzweil's version of Moore's law? This is sometimes called the 100-year version of Moore's. Please raise your hand, because I'd really like to know how many people have seen it. I would guess 25 to 30% of the room. That's slightly above average. One day I'm hoping all the hands go up, because I used to say I think it's the most important graph in all technology business, and I think it might just be the most important graph ever plotted. Just to let it sink in. I'd be curious afterwards if anyone can think of a more important graph that's ever been plotted. What you see, just in case you're wondering, is a logarithmic scale, right? So this is not, this was semi-log paper. So, a straight line would be an exponential curve. This is arguably a double exponential based on some independent analysis by SFI again. And what you're showing is the dots are the best price performance computer of their day. This includes, device that took the census in 1890, the relay-based computer that cracked the Nazi Enigma code in World War II, the vacuum tube-based computer that predicted Eisenhower's win. Nobody knew they were on the curve at the time. So what Gordon Moore observed in the modern semiconductor era was a refraction of a much longer and profound trend that humanity's capacity to compute has compounded for as long as we've been able to measure it, right? Perhaps forever. And hence, it might just continue to, right? I mean, a safe bet, if you could make any bet in technology, is this might go on for another 5 years, despite what Intel says, right? So Intel, by the way, has not really been on this curve for the last 10 years. To be on this curve for the last 10 years, you have to look at NVIDIA and the GPU market, the graphics processor units. And that will actually relate to this panel because that's what most or many of the cutting edge researchers use as their actual computational engines for deep learning, at least today. Now, that has an impact on a lot of industries. I mean, a whole side thing is that betting on Moore's law and what industry will next fall prey to either a simulation science revolutionizing it or the use of deep learning methodologies to restructure the industry. We're seeing it play out all around us, right? Whether it's autonomous cars, whether it's new ways of designing food and microbes that make fuels and chemicals. This is where we're seeing industries that traditionally weren't open to entrepreneurs or venture capitalists. They were capital intensive. They were staid, boring businesses with almost no change over decades. Certainly no major new entrants. Take the automotive industry, right? Not an IPO since Henry Ford. And then Tesla comes along. Same with, of course, a variety of others that we all love and hold dear. Now for something completely different. Let me just give you a couple of teasers before we go to our panel. I was just meeting with this company, And this is a quote from the Time magazine. I like this. David Deutsch, the Oxford professor, referring to this, perhaps the first time we can make something useful with parallel universes. Because, you know, they're out there. I mean, let's put them to use, right? To actually engage refractive echoes across parallel universes to do computation. Well, that's pretty mind-bending in its own right. But well, how does it apply to this? Well, lo and behold, this guy Hartmut Nevin at Google has been using the D-Wave quantum computers for quite some time now, over 5 years. And in 2009 at the NIPS conference, he shared that it's already outperforming the computers in the Google data center. But everyone just ignored him and kept saying, nah, you're smoking dope. There's no way that it's actually doing that. And I love that quote. It's sort of so provokingly fetching. But for the panelists who can't see it, they basically say that quantum machine learning may provide the most creative problem-solving process under the known laws of physics. So I love that. Maybe there's unknown laws of physics, or maybe there's other, gotchas. But in any case, the point is just they've been using it in this sort of image recognition task, the things that power, like when you wink for Google Glass, all these really sophisticated applications like that. And that's kind of interesting that they're saying that. And that, by the way, they now are on a machine that's 50 times bigger than the one that they made that claim in 2009, and they're about to buy one that's quite a bit bigger still. So why is that interesting? Well, these things scale unlike traditional computers, but they also map very elegantly to deep learning networks. In fact, skipping all this stuff, basically, you could think of each of the qubits in this architecture, specifically an adiabatic computer, when you're doing one of the flavors of deep learning, a probabilistic kind of model, where you don't need to do a bunch of random samplings where you approximate a probability distribution by just running an experiment many times with a deterministic random variable. You, in fact, represent in each one of the qubits the probability distribution that each neuron would be at, and each of the weights is literally the connections or couplings between the qubits. So it might lead to a huge step forward in this, but it's not yet shipping outside of Google. Google's figured it out. The world at large hasn't, not even D-Wave, but they're working on it, trying to make that available to others. So last thought before going to the panel. Yes, and I think I'm just at the end of my 20 minutes. If I step back a moment, and even if nothing about deep learning interests you, it is an example of a larger family of what I call iterative algorithms, where you do something over and over again, and you get some wonderful results. And if we look at some of the categories, these broad categories up above, it begs the question, will we design these complex systems that exceed human understanding through traditional design methodologies? I don't think we can. I think the only existence proof, both in the computer science era of today as well as biological evolution over eons of history in time and space, shows that if you want to build something big and interesting and complex that we don't understand, like the human brain is not understood by the human, right? That is only so far been done through these kind of iterative algorithms. But they have some implications. I won't go through this one other than it's a pretty picture with lots of moving parts. To say microbial metabolics are complex, you could try to design a microbe to do what you want. We've invested in a lot of companies that are trying to do that. Or, as one company did, you could selectively cripple it so that it makes the chemical you want as a byproduct of its own evolution and survival, and then just keep breeding them, because they reproduce like crazy, and skim the fastest growers, and at the end of the day, you had, in fact, a 20,000-fold improvement over human design methodologies just by artificial evolution. The problem is you didn't understand what you had evolved, you just knew how you evolved it. And that metaphor, if you think about that as a story, is very complementary to what you see in neural networks, at least. That, it's an inscrutable black box, and you can only understand its process of creation and the interfaces you use to generate it. In fact, I could show that with this slide, that all these things on the left, biological evolution, cellular automata, if you're a fan of Stephen Wolfram, genetic programming work both in literally analog circuits and physical antennas that have been done where you sort of breed designs over iterations and then test them with a test function, or when Danny Hillis did it with a bubble sort alternative, his own evolved sort algorithm, or neural networks back in the 80s, or quantum computers in general. In all these cases, you have an iterative algorithm that generates really powerful designs, many of which are patentable and exceed human capabilities, but no one understands why they work, why that antenna works, what is line X of an interesting cellular automata. There's no way to jump to the answer, no way to shortcut the computational complexity of it, no way to reverse evolution, if you will. We talk about reversing designs, you can't reverse evolution. It's not apparent. And so here's the last thing. The generalized implications, I think, that might be interesting if panelists will disagree with any of these later, is that in general, a lot of these methods, you end up with a black box defined by its interfaces. Most importantly is this third one down. I think the locus of learning, meaning what matters for people in this field, is how you build things, not what you build. You don't tweak the end products, you tweak the process of their creation. It's just like parenting, right? You can't say fix the teenager. The best you could do is give advice to the next parent on what they might want to do differently the next time they raise a teenager, as a metaphor. I think that might be the simplest way in lay terms. That's the kind of a level I want you guys to abstract this to. And that's what we perceive as beautiful, I think, is computational complexity, at least in this universe, because the whole quantum computer thing would throw all of this out the window if it works. That's why I'm excited to see if it does. So last quote. Danny Hillis wrote a book on computer science, Pattern on the Stone. Last page really is, I think, the most fetching comment, is that really what we have upon us is a grand engineering challenge to be able to build more than we can understand and to transcend engineering. So I'll leave it at that. This picture I took of a black swan drinking out of the fire hose is my mental model of this world that we're about to enter. And let me now, briefly, as our next speaker gets ready to come up, and I'll introduce him last, but I don't know if you want to go and sort of just stretch and do your stretches. Let me just mention who's on our panel so you know who we're going to be hearing from tonight. And I'll go in reverse order. We have, actually, the person I know the best, Naveen on the far right, is actually the most recent investment that I've made. So full disclosure, we're an investor in the company. We just had our first board meeting, so I know a little bit about what he's up to. But he most recently came from Qualcomm's neuromorphic computing group, and so did some of his co-founders. And before that, he did a PhD in neuroscience, but before that, he had a 12-year history designing chips for Sun and other companies. So he started in the chip side of the business, got fascinated by the brain, and then went recently from Qualcomm to start a company that's going to build hardware solutions to accelerate, hopefully, everything that you hear about today. So it is possible that there's a better way to do the physical computation that underlies these kinds of algorithms. Then we have, I believe we have, is it Ilya? Is that right? Yeah. Okay. Ilya is going to be fascinating because he comes to us from the Google Brain Project. Before that, he was a student under one of the most well-known folks in this field, which is Geoffrey Hinton up at the University of Toronto, and that's where he got his PhD, and then started a company, co-founded it with Hinton, that was acquired by Google, and specifically in the area of visual object recognition. And he'll tell us a bit about both Google Brain and how they're thinking about this from a Google perspective. Then we also have, I think last is Elliot, right? Yes. So Alchemy API, which he's the CEO, co-founder of, is very interesting. They're offering deep learning as a service. So if all this is like mumbo jumbo, but you want to like incorporate it in your business in some way, he would be someone who would be delighted to try to provide that capability. And that'll be an interesting topic that we'll cover on the panel is, how much of a geek do you really have to be to take advantage of some of this stuff? Before this, he was CEO of other companies in network security and intrusion detection. And then lastly, let me mention Adam, which is going to give us a 10-minute talk on his company. So I won't mention what his company does, but he was the CTO, he is the CTO of it, and it's a machine learning image recognition company. Formerly got his PhD in EE from Columbia and worked for Google for about 10 years on the music recommendation products for Google Play, Google Goggles, and a whole bunch of things that relate to visual search and obviously play straight into this area. So with that, let me give it to you. And good. I think I only added 2 minutes to the schedule there with the intros.
Good work. That's not easy.
Go ahead.
Thank you very much. It's pretty awe-inspiring and humbling to be here talking about such an obscure backwater of computer science. It's only at Stanford would this be a packed house. So I want to try and make a few points in the time that I have, and hopefully leave you with some more questions that we can address in the panel. We can't really talk about deep learning without talking about data. It's, in some sense, deep learning is nothing more than what happened when machine learning hit big data. To me, I think of data, these days I'm thinking of data in a dichotomy of, there's really two kinds of data. There's data that's recorded from the physical world, and that's including photos that we take and videos, audio, telescopes, and physical sensors. And then there's data that we humans produce. And really, to a large extent, when we think about big data, text processing, and all the things that the world of computing that we know and love, search and sorting and filtering and crunching numbers and computing statistics on meaningful data, things that have meaning to us humans, at some level that was eventually, ultimately had been typed by somebody somewhere. So this is my, my intro slide here is a little meditation about data entry. Data entry started as, sort of a specialty that was done in a few organizations in the world that had access to computers. And I guess, if you really go further back, you go pen and paper stuff. But let's start here. And then there was a democratization period where, starting with the personal computer era and accelerating vastly with the advent of the internet, where everyone was producing data, typing text messages and tweets and sending email and contributing to Wikipedia. But all of that stuff, had to be filtered through a human brain, right? This is like, you can't simply, or until recently, put a computer in front of the scene and say, describe what's happening. And so my distinction that I'm making here is something that that we're focusing a lot on Clarify as one of the main opportunities that's coming out of deep learning. And that's basically bridging this gap between the physical world and the world of computing, the world where the algorithms that have been studied and we have such computational horsepower and huge data centers across the globe to operate on, bridging that gap from the world that we actually live in. And so, moving past just kind of recorded data about the physical world that you can only do except sort of play it back. And now we're getting into a world where we can take measurements of the physical world in terms of pixels hitting the CCD in a camera, and then turn that into symbols that we can use to search and sort. So that's the sort of high level of one of the opportunities that deep learning is kind of opening up, and I'll explore that a bit more. Let me show you what I mean. So let me just run a demo. Always a bit of a risky endeavor. The Wi-Fi could fail. Is this big enough? Yeah, good enough. So this is clarify.com. You can try this at home. And we are an image recognition machine learning technology company. And so what we've been working on is a way to take an image and produce meaningful description. So forest, fog, mist, path, road, tree, foliage, park. This took 80 milliseconds on some GPU in Amazon. And we have this other technique where we can use the same neural network that has done this feat and use it to find similar images. And you can see that this image similarity is a very sophisticated mixture of semantic, high-level similarity of concepts, other paths and mists and trees and forests, but also sort of compositional and visual similarity. Let me just throw a couple more in here while we're playing. So I'm going to increase the font so maybe you can see a little bit better in the back. Automobile, vehicle, car, even things like Volkswagen. So there's potentially, there's lots of different ways to describe a scene. Some of it is very specific, like Volkswagen, and some of it is higher level. And we can also do, different types of images. So here's another car. And of course, I have to show a picture of my kid because that's my responsibility. Kids, children, clown, it picked out, and even things like fun, right? So this is not just objects and but sort of emotional descriptions. And let's talk a little bit about how this stuff works and then why it's exciting. So, am I back? Okay, deep learning tutorial, the 2-minute version. Steve actually covered a lot of this, which is great because I was never going to get through it in time. So the neural network, he showed some part of this already. At a high level, like I said before, deep learning is really just what happened when machine learning hit big data. Machine learning is a particular approach to a very basic computational task we try to do with pattern recognition, mapping some inputs to some outputs, some signals or some features gathered from somewhere, and some label or name or tag in some sense, but you can also do prediction and other types of things. And machine learning in particular is an approach that is trained. So the work of the algorithm designer is not finished when they're done writing the code. You have to then throw a lot of data at this thing and to get it to work properly. As Steve was showing, you presented a lot of examples, and the neural net might have some initial, basically you start with these things completely randomly initialized. And then the weights, the weights are really what stores the knowledge that the neural network has. And if you show this thing a Lamborghini and it says that it's a duck, you penalize the weights that were active and contributed to that erroneous label, and if it gets it right, then you reinforce or reward the weights that contributed to the correct answer. The Clarify version of History of Neural Networks has to include Jeff Hinton and Jan LeCun, because Matt Zieler, my co-founder and CEO, was students of both of these, so sort of like our pedigree. But you know, they and other great researchers. Jeff Hinton is now, by the way, was Ilya's professor and sort of formed the core of the Google Brain team. And after some initial early successes in the 80s with the neural networks, there was a bit of the dark ages where they were getting beat by other techniques. And this is interesting because I think it's contributed to the situation that we have now where it's quite a, basically an arms race that's going on. Because once GPUs and the availability of very large data sets hit, and these algorithms started just beating the pants off of everything else, 15 or 20 years had passed where no one was really doing this research anymore, except for Jeff's lab in Toronto and Yann LeCun at NYU, Yoshua Benju at Montreal, and some other places. But something about Canadians in deep learning. I don't know if anyone can explain that, by the way. Matt, my co-founder, is also Canadian. Yeah, so there was a relatively few people who understood this stuff, and then to have such a broadly applicable technology that was suddenly succeeding so wildly at doing quite sophisticated things and having such a few number of experts that understood it, that's kind of what led to this, the talent grab, where large tech companies sort of said we need to know how to do this stuff, and sort of acquiring or acqui-hiring or otherwise recruiting their way to deep learning expertise. So no deep learning talk, at least in my world, is complete without talking about ImageNet. This is just, it's the baseline, it's the benchmark in large-scale image recognition that has been used over the past couple of years, and you can really measure, the deep learning, the impact of deep learning here. So if you can see, the orange dots are entries in this competition. So the competition is you get 1 million images, and there's 1,000 categories you have to recognize from the images. So the first couple of years, there was, so this is error rate, so lower is better. So down here, these are the winning entries, and there was not too much improvement from year on year. There was some iterative improvement. And then in 2012, Ilya and Jeff Hinton and Alex Krzyzewski blew everybody out of the water with this little orange dot. And you can see, the performance gap here is just huge. It's left everything in the dust. And the next year, everyone's on the bandwagon. And then, and by the way, this little dot down here, that's the winner. That's Clarify. And last year, and this year, Google takes the prize. We didn't enter, but you you can see that everybody, even like all of the entries. First of all, everyone's using deep learning, and also everyone is beating the best traditional computer vision results from only 2 years ago. So this is the kind of performance jump that you see every 15 or 20 years in the field, and this is like what gets people really excited, and on such a very it's like basic capability of computers. This computer vision. This is adding a new primary sense to machines. Yeah, this is a convolutional neural network. It's the particular type of neural net that is succeeding in image recognition, and we'll get too deep into the technology, but it's a particular way of arranging the neurons so that they do a trick that gives us shift invariance. So you don't care where in the image the boat or the duck or the whatever else you're looking for is, and so the convolution is basically just sort of sliding a filter or a template looking for a particular thing that it's been trained to look for. It sort of slides around the image, and that gives you scale shift invariance. And other invariances are handled by other parts of this network. But the basic point is that we're using a lot of layers, way more than we used in the 80s, and the number of parameters is orders of magnitude more, and we can have numbers of categories and classes that can be recognized by a single network. In the old days, the early neural networks that were so successful in speech recognition and handwritten digit recognition for the postal codes and used by the post office was another famous example. There's 10 classes. There's 10 digits that you have to recognize. The model that I was showing in our Clarify demo, that's 10,000 different things we can recognize. That's getting, an average adult in English has around 90,000 words, not counting personal names and other things like that. I want to focus, I'm going to do a little sort of pretty picture show, but Steve talked a bit about this idea that the neural network and some of these other deep learning techniques are a bit of a black box. Actually, with neural nets in particular, and some of the research that Matt did as a PhD student, we can peer into the black box a little bit. So first of all, I want to point out a couple things about this part in the lower right hand. So these are the filters, the first layer of filters that were learned, the convolutional filters that were learned. In this case, it was trained on ImageNet. And there's three mind-blowing things to say about this. One is if you train any neural network on with large enough data on real-world images, they're going to learn these filters or some close approximation, the same filters basically. Two is that they very closely approximate some well-studied mathematical functions, Gabor wavelets, and it's pretty well understood why these things are good at representing images from a theoretical point of view. But they were just, they started out random, and the neural network found these. And the third crazy thing is that neuroscientists, can poke into the brains of animals, into the visual cortex, lower levels, and find, specific neurons that react just the way that some of these individual filters do. So biological evolution and neural networks and mathematical theory have sort of all converged on this particular solution to the problem of recognizing scenes in the world. So these other things here are basically showing small patches of images that respond strongly to these filters. And so if I go, oops, wrong way. So this is layer 2, and it's showing what the filters have learned. You can see there's more complicated gradients and curves and some checkerboard patterns. So now we're sort of able to compose those basic filters and then say, okay, there's gradients this way, gradients that way, and you get a checkerboard. And then if you go, I'm going to go up a level. This is layer 3. Now we're actually starting to see parts of objects and sort of spokes that look like a wheel. And what we can do then is kind of overlay patches from images that again strongly light up when those filters are active. And you can see, so basically there's 9 by 9 grids here. Right? So let me see if I can find my mouse. But there's clearly a dog detector down here that's finding, here's the husky detector. This is actually layer 5. It's near the top of this particular neural network. And so we've got a husky detector, some sort of flowers. And so this is kind of a way we can sort of see what's happening in the black magic. Like Steve was saying, we start with very simple things. You can compose them and to get higher and higher levels of meaning, basically, as you go up and building on the layers before. And at the end, you can start to recognize things like I showed earlier. Yes, I am over time, so I'm going to whip through this. What is it for? And we can spend more time talking at the panel. But if you're like me, you've had the following experience many times over the past couple months. You want to show somebody a picture. Maybe it's your kid or a vacation or some work you want to show to a client. And you take your phone out and you just start scrolling through, and it's buried. And so this is one example of the problem of just overwhelming number of images that we are producing or that we encounter in our lives today. And this occurs over lots of different domains. So consumer photos, but also e-commerce and shopping, particular verticals like stock photos and other review sites, all kinds of things. Ad targeting, once you understand what's in an image, you can target ads instead of just based on keywords. And then there's lots of specialized domains, satellites and medical, et cetera, et cetera. And you can take a large image repository, which is completely untagged, and then do stuff like search for beach, sunset, jump. So I just want to leave you with one more thought. Tying back to my earlier discussion of data entry, the next step after data entry is action in the world. First you get data in, and then you do something. And one of the exciting opportunities I think that this stuff is enabling is there's this vision of we're all carrying these cameras around soldered to a GPU. And this thing can become like the mouse for the physical world. It's the thing you use to reach out into the physical world and take action in the world of computing with it. Right? It's you point and click, point and snap or whatever. But you see something and you click, do something to it, share it, search for it, buy it, whatever. And I think that's the deep learning is forming that bridge between the physical world and the world of computing, and hopefully we can keep chatting about that.
Adam, yes, come join us.
Email me.
Great. So now we're going to enter the discussion here on stage, and as you know, as you heard earlier, we'll save the maybe most interesting part of the conversation to take your questions, which I'll see here on this device when we switch to that part of it. So feel free to submit questions at any point, and they'll be moderated and such. But since we haven't had a chance for the other three panelists to introduce themselves, why don't, if you can, try to limit it just a couple minutes, if you will, just so everyone has the context. What is it, again, that you do in your current company, just the current company? And if you want to, go ahead and segue into what do you think is the most exciting thing about deep learning right now? Either that's why you started your company, or it's what you see coming just down the pipe. But that could be some of the fodder for the questions that follow. So maybe I'll just start down here with Nirvana and tell us a bit about it.
All right, so thanks for the intro earlier. My name is Naveen Rao. I'm the CEO and co-founder of Nirvana Systems. We have a slightly different tack we're taking than many of the deep learning companies that have been out there. We're approaching this from the hardware angle. And at first blush, people are like, well, there's commodity hardware. Why would you be approaching something from this angle? There's really some very interesting things going on in terms of computation. That's actually what excites me about this the most, is that deep learning is really providing this infrastructure, this mathematical framework to make sense of data. And actually, it's a form of computation. It's a computational paradigm, if you will. A bunch of nodes doing something in parallel is actually very different looking than a traditional computer. And so this is kind of that missing link I think we've all been looking for. It's like, how do we really start recapitulating what a brain does and how it does computation? And so that's kind of what's driving us here, is that we now have that structure, and we can actually start moving computation in a whole new direction. Instead of doing fixed mathematical operations very fast in a very precise way, we can actually start thinking about the fuzziness of it. Data, when we look at big data, like very large data sets, we don't care about exact results. If you look at the stuff that Adam presented a moment ago, it's probabilities. It's like 70% chance of this or 20% chance of that, and that's really how an animal perceives the world, right? So this is kind of what it's sort of a binding theme for Nirvana, is that we can start taking advantage of these algorithms and start building very interesting new hardware, taking computer processors in whole new directions. And this is something I've been thinking about for a long time. I spent a good part of my career designing chips, designing processors, and then I went and studied the brain to understand, what is biology doing? So one statistic that's always very striking is that human brain uses about 20 watts of energy. Your laptop sitting on your lap probably uses about 50. Presumably, your brain is doing more computation than your laptop. So what are we missing, right? It's doing many operations in parallel. It learns, it adapts, it changes. So this is what's really driving us here. And now it's a very interesting time in history, because not only do we have the algorithms, we have the data to make those algorithms work. We need tons of data to really train these things. And now there's actually business cases. So you can't actually build a piece of hardware or a piece of software, for that matter, without a business case. And so we're actually at this point in time where we have a case. We have tons of data. We have use cases. And we really need to scale these things up. And so now we can start taking a step back and looking at what does biology do from 3.7 billion years of evolution to arrive at a mammalian brain. And so not that we're building something that's neuromorphic, but we can take some cues from that. And that's kind of what's driving me forward.
Great. Well, that might be a good segue to Ilya. If you're working on something called Google Brain, then perhaps this metaphor rings true as well. So I'd love it if you could tell us a bit about your work there, work in translation. And I don't know if you want to segue off the concept of custom hardware to accelerate this. I'm not sure if that's something you've looked at yourself, but if so, feel free to touch upon it.
Yeah, thank you. So that's right. I work at Google Brain, and I do research on neural networks. And the reason neural networks, and as it's now called deep learning, is so exciting to me is because it actually works, as opposed to a lot of other things that didn't work. And it works in a very certain situation, but once you get the situation, it works really well. And it works whenever you have a lot of input-output examples. So if you have a lot of inputs and you know what outputs to give them, then you can get a neural net to imitate, to understand what is the real underlying regularity in the data and make good predictions. Like, for example, in object recognition and also speech recognition and also machine translation. And what's really nice about neural networks is almost, for me, I find neural networks, the work that we do, is very philosophically satisfying. Because we have those extremely simple ideas, the simplicity of, so it may seem that because we have these programs that do very complicated things, that the programs must be very complicated as well. But that's not the case. We have very simple ideas and very, very simple algorithms that almost magically manage to produce these extremely complex results, very much like evolution. The ideas of neural networks are almost as easy to understand as the idea of evolution itself. It's slightly more complicated. There is a little bit of math you may need to know. First-year calculus, a little bit of probability, but nothing terribly sophisticated. And these simple ideas, which were invented in the 80s, all of a sudden, they begin to work. And also, I want to just make a comment about big data, because I think it's important. Why do we need big data? Big data is powerful. We all feel it. But why? And the answer is the following. If you want to solve a hard problem, chances are you need to use a big neural network in order to solve it, because a small neural net can't really do much. And if you need a big neural net, you need a lot of data to train it. And now, as for the things that I'm working on, the things I'm excited on, so yeah, recently I was working on machine translation. I was working on methods that can map sequences to other sequences, which is an important special case. And now I'm looking more into things related to unsupervised learning, which I think is extremely important. Can we learn without labels? And reinforcement learning as well. So I think that we will see a lot of nonlinear progress in the future, and it's a very exciting field to be in.
No, I'll come back to that later. There's a follow-up I want to ask you, but I'll make it a question for everyone on the panel. So just to be fair, let's hear a little bit about Alchemy API, and this will be a segue to the question I want to ask next. Just tell us a little bit about what you do, what you're excited about, but hopefully segue into making it available for everyone else, right?
Absolutely. So I'm Elliot Turner. I'm the founder and CEO of Alchemy API. So our company's mission is to democratize deep learning to be applied to the world's business problems. So we're working across 10 different industries today, everything from advertising to financial services to business intelligence, helping corporations apply this revolution in algorithms to their specific business problems. So the interesting thing about us as a company is most of our customers don't actually care about deep learning. What they really care is what comes out of the box. They care about the outcomes, the results. And so, we hear a lot in artificial intelligence that they stop calling it artificial intelligence once it works. I look forward to the day when people actually stop talking about deep learning, because that's when we feel the field has succeeded. I cut my teeth in the 90s in the network intrusion detection space. We helped invent the technology. And so I really approach everything from a networking perspective coming out of that field. And so when we think about AI and deep learning in general, we think about it from the perspective of a stack. We really like to refer to it as an AI stack, very similar to a networking stack, where capabilities build upon capabilities. So at the bottom of that stack, you have the ability to understand language, understand images. Then the ability to apply that at scale from predictive and other standpoints. Then finally, asking questions of that data, or even being told about what questions you should be thinking about. So these are the things that excite us. So we're applying deep learning from everything to natural language processing to image recognition to question answering from raw natural language text.
So this might be a good segue, and at this point, anyone can jump to answer, but I'll try to set up what might be a dichotomy of opinions, I hope, as opposed to kumbaya, everyone's on the same page, between the Borg, the power of Google, Microsoft, Facebook, Baidu, in their domains versus everyone else. So on one hand, I could see the argument. In fact, even Ilya, in his early work, was a small team, world beating, right? The Kaggle competitions, all these different contexts. You have small groups of 1, 2, maybe 3 people beating all the history of computer science, which is kind of interesting. Those might be the early movers, though, applying these techniques in a new domain. I'm wondering in the longer run, does value and strategic leverage shift to those with the data, with the I/O examples that you were referring to, Ilya? Those with access to compute, well, that might be democratized, perhaps. But the subtle question I want to also ask is, what about the process learning? So when Google has been and continues to be at the vanguard of this, as do a handful of companies, they learn a lot about how you build these things, what works, what parameters, how to tweak this, that, or the other aspect of it, not all of which is published. You will offer your services, as you just said, Elliot, to everyone, and they want the product. They don't care about the process. But if all of your customers have zero visibility into the process, they become more and more dependent on you to keep up, right? So if Google or some other competitor does better than you, they're kind of stuck at ground zero. So I throw it out at first as, would any of you agree or disagree with that framework? And then, which side would you bet on? Consolidation of power around these technologies, or empowering the small guy?
I can address part of it. I probably want to rephrase one aspect of it. I don't necessarily think it's the data per se, it's what the data can enable. It's really what we're selling is intelligence, right? I mean, I think from the beginning of time when humans were educated, we started selling intelligence, right? We sell skills. And so that's kind of the same thing that I think is going to be happening in the future. And so data enables one to build a network or a machine that has skills. And so that's really what we're selling. So democratizing the platform or the data.
To be fair, I think you could defend that, hey, we sell arms to everyone. We sell hardware accelerators. That's the ultimate goal, so that everyone could be as good as you know, somebody who's got their own data center.
That's right.
So I think you could make that claim, and that you're incredibly so. And similarly, you provide the software algorithms. But I'm curious, does that atrophy the core? I mean, in other words, as you think about what gets you excited about this field, can you envision a world where companies that are competitive using these technologies don't themselves understand anything about how they work? And, you know, will that be, you know, a platform stack that just, you know, you and others provide? Yeah.
My perspective is that data is huge. Data is core to making machine learning succeed. But there's data in a lot of places. It's hard to compete, you know, with Google if what you're trying to do is, you know, email prediction or something like that. But there's a lot of nooks and crannies that Google is, you know, not remotely within the realm of their business.
Fair, I don't mean to imply, and Ilya's probably like, what am I supposed to say now? Only if you were trying to go against Google in an area where they had the most data, right? Clearly, there's a wide open field, but then there might be some other company, whoever has the most data, if they had a proprietary lock on it, does that afford an advantage that's now more powerful than ever before?
I think what happens is two things. So there is, there's advantage to people who have more data, but there's also ways, you know, I think that, you know, data can come from different places. You can have your own users. You can partner with partners who don't have the expertise, but then you make a trade. We give you expertise. You give us data, and then, you know, you can build your own products that compete, and you can get data. It's also an unanswered question, I think, of how much data is enough. You know, there might be some threshold where, you know, for this particular problem, I think it's very problem specific. This particular problem, you know, you got, you know, a corpus of 10 million emails, 100 million is not going to do it for you. I actually think that problem is harder, but
like you might say, images. We've got plenty, right? I don't think it's for lack of images on the internet.
And then the other side of it is that just going back to what you were saying before about the expertise. You know, it's data, it's compute, and it's the actual, you know, you say process learning, but. I think that's, you know, it's a continually expanding sphere, and so the sort of last year's techniques kind of, you know, they get published and then other people do them, and hopefully, you know, by then you're kind of moved on to the next thing, and always, you know, adding tools to the tool belt and getting your magic stuff to be even more magic than what was there before. So that doesn't really answer the question about is it a good thing or a bad thing if all the expertise is kind of accumulating in a couple of the big companies, but I think it does. You know, it points in a direction for even the small teams that, like myself, you know, who sort of have an early stake in the game to kind of, you know, continue and ramping up, because as other people catch up, we can hopefully, you know, get a little bit further ahead. From my perspective.
You know, one of the things that excites us about the field of machine learning is we're seeing a real transition point. You know, machine learning, despite the word machine being in the name, historically had a lot of human involvement. And it relied on the innate cleverness of individuals through a process known as feature engineering to translate raw data into something that traditional shallow learning algorithms could more effectively deal with. And so we're seeing now a real change, a shift towards these more automated approaches that really can learn directly from raw data in a fully unsupervised way, or maybe weakly labeled data, these distant supervised and other approaches. And so, you know, we view this as a huge disruptor, because instead of, you know, piling a bunch of PhDs in a room, kind of building up this human advantage, you can really focus on some core algorithmic breakthroughs and getting data, but not necessarily all data, the right data. And there's some interesting data points now that are coming out of the field. You know, if you look at the work that Facebook's been doing in face recognition, for example, you know, they tried accumulating 1 billion faces from different profiles and training up a model there. They also tried trying to create a very hard data set of people that looked pretty similar to one another. and found that that system, despite being trained on far less data, outperformed the one that was trained on a lot. So I think it's a matter of not simply stockpiling and accumulating this.
Honing the algorithm on what look to be similar faces.
Absolutely.
Interesting. I mean, I'd love to hear a Google perspective, and I'm not sure. Well, first, let me ask, should I reframe the question, or did you have a thought that you wanted to share in response to that?
I had a brief thought. I just wanted to say about the notion of consolidation of talent in large companies. I think that it's unlikely to happen because what you'll see happening now is a lot of students will flock into the field, and there will be enough of a supply of talented, qualified people that could build these systems.
Right. I think that is probably true. I'm curious, perhaps, as you know, from an inside Google perspective, some of you have been there before, some of you are there now. Does it make sense, as you were, like some people that work for Google try to make sense of everything that's going on around them. Why did we just acquire 7 robotics companies? Why did we just do that? You know, what's the grand master plan is a recurring question. And other than a march towards some AI future that Sergey and Larry had talked about long before they went public, it may not always be clear, but as an outside observer, it seems to me that it all snaps into place if we think of, you know, ad matching and just about everything that makes money for Google relates to and can be made better through these techniques. Even if you have folks working in translation or in image search, which is, again, of course, the core product, if you improve the general algorithms around deep learning, I guess my question would be, how fungible do you feel that they are? So like whatever work that you're working on now, if you make a breakthrough in the way in which you do basically any kind of breakthrough, do you think it would apply and benefit other groups working on other deep learning projects in different domains?
So this is an excellent question, and the answer is very much yes. In fact, the reason this deep learning is having so much attention is precisely because it is domain independent. So in other words, you have a neural network, and yes, it's true that you need to put a little bit of domain knowledge into the neural network, but it's a very limited amount. So what ends up happening is that if you come up with an advance of how to train a neural network with less information, then all of a sudden, every single application of neural networks can benefit from it. If somebody comes up with a very good unsupervised learning algorithm, then again, every single application of neural nets will benefit from it. So yes, these algorithms are extremely fungible.
Yeah, and I'm glad to hear you say that, because that does make a little more sense than why would it make sense to acquire raw talent, even if it's in robotics or in a field that at the current moment may seem a little farther afield, because there is a unifying theme. Yeah.
I want to add one thing. It's actually, I mean, I've been in the industry for a number of years now, and this is actually a very unprecedented time in terms of openness. Google being part of this, Facebook, all these companies have very large deep learning, machine learning groups, but never have I seen industry be so open and publish their work so readily. It's very interesting to me that, you know, the traditional thing is like, you know, you've got a CPU and you've got some architecture and it's all hidden details, all under NDA, this kind of a thing. That's sort of the traditional model, right? You got some software, you have your secret sauce that makes it what it is. And that's always been the protected secret, either patented, trade secret, what have you. What's happening in deep learning is these innovations are coming out, Google or whomever else is publishing them to the open community, right? They're deploying them in their own problems. And it's just a very interesting time that I've never seen something like that. I just don't know where it's gonna go, but I think it's just, to answer your question earlier, it's going to lead to advances for that reason, definitely, because that information is being shared very readily. And I wonder if that has something to do with the fact that so many people are coming from academia and then going to companies. They still keep that mentality, which I think is a great trend.
I think it's also related to the fact, I think that they wouldn't, it's not pure magnanimity. I think that there's, you know, it's partly to attract talent, right?
Right.
I mean, look at the great work that we're doing here. And it's, I think, also based on a confidence that it's not so easy to reproduce, even if you know how to do it. Because you need the data, you need the huge amount of compute. And I think that there's a little bit of that goes into the calculus, I think. You know, Google's, you know, there's plenty of secrets that Google keeps. So they're, you know, judicious about what they share. It must mean something. But you're right, it's quite amazing now.
I want to ask one last question before going to the iPad, so last reminder if you want to get one in. That fascinates me. You know, but as I think about why I first thought this field was fascinating when it actually didn't work, and I started a PhD actually in this field and gave up on it in the 80s, was the way in which it seemed to recapitulate biology, right? That there's these existence proofs, and when something seems daunting, it's nice to know that it happened once before. This idea of mimicking the brain, the fact that we call them neural networks in the first place, and there definitely were some analogies that were in there. Today we heard Adam express, and I have similar moments of just marveling when one of these networks, has edge detection, like just like an infant would in its first moments when it doesn't have labeled data, it just sees the world, and there's certain things that evolve or sort of develop first in the way that synaptic pruning takes place, and then lo and behold, in these artificial networks, you see that low-level construct. So my question is, it could be one of two, you could take either one, but I think they interrelate. One is, do you think the long arc of this, as you look out 5 to 10 years, will recapitulate biology itself, in that we start with a sensory cortex, perhaps a reptilian brain, then layer on just tons of memory and have a frontal cortex and all that, just like the primate to human, or just frankly the whole stack of brain development. With some of these techniques, it seems almost as if some of the researchers, whether they're those who are trying to build AI products, and there's a couple of them that got a lot of funding recently, we might make that argument that we'll bake in those layers, then the next layers, as if we know enough about the brain to mimic it. So I'm curious if you think it will either in a supervised or unsupervised manner, meaning in a directed, or just is that the way it's just naturally going to go? And then if that's not really what floats your boat, as you look out 5 to 10 years, do you think in some way, though, this is a path to AI? And if so, and if it doesn't mimic the brain, will it be an alien intelligence that we, frankly don't understand one bit? Or what does that lead to? And if none of those interest you, what do you think it does lead to? What does this take us in 5 to 10 years, which is, of course, infinite in technology timescales? So anyone who wants to jump in first, but I would love to hear a short thought from each of you.
Yeah, absolutely. We see a trend from focus entirely on human-labeled training data to more unsupervised or weakly supervised approaches. And I hear a lot about unstructured data in the world. I'm personally not a huge fan of the term, because if you look at the world around us, if you look at language, if you look at the visual world, there's innate structure in everything. It's all about teasing that structure out and finding the meaning that's latent in the world. And ultimately, this is how people learn. This is how animals learn. We're not entirely reliant on human trainers to help us propagate intelligence. So, when we built our vision platform, we took a slightly different tack than a lot of folks. We did not use labeled data. We pointed the learning engine that we built for language at the web, crawled hundreds of millions of photos, and using a more generative approach, built out a system that could discover concepts on its own. Cats, dogs, houses, trucks, the things that people find important because they're taking pictures of them. And I think we're seeing this now spread into the world of language with these pre-training approaches that rely on the innate structure of word ordering, of semantic similarity between words that is the way we all communicate as people. And we're going to continue to see this applied to lots of different problem sets to ultimately magnify what's possible. Because the reliance on human data, just like compute, is a scalability challenge for this technology. And if we can take that out of the process and really use all the wealth of data that's already out there, it's really going to open up new worlds.
So I can give one answer to this question. So there were two parts to the question. First part is whether our neural networks will keep on looking more and more like the human brain, and the second question is how things will look like in the future. So it's obviously very difficult to predict how these neural networks will evolve. I think it's plausible and likely that they will be a part of whatever really intelligent system that we will build. But whether these systems will be like the brain or they'll have some substantial differences, it's very hard to tell because we don't have any idea of how to build these things right now. However, one thing you can tell about the future, so I think you can still make useful predictions, or at least an understanding of how the future will evolve. If you look at our neural networks, if you look at our deep learning systems, you will see that there are two conceptual parts. There is the first part, which is the neural network itself, which is the thing that gets the knowledge, the things with the connections, the thing that does the computation. And the second thing is the learning principle. At present, we have mastered only one learning principle really well, which is the supervised learning, where we have inputs and output examples. And you can have innovation and progress in both of these areas. You can come up with more powerful neural networks which are more like general computers, ones that can express general computation. And the second area of progress will be in learning principles. So we will be able to, eventually we will understand how to do good unsupervised learning, how to do good reinforcement learning, how to train those systems, how to train a system with minimal amount of supervision on very complicated tasks. So both of these things will need to progress. And I think it's harder to, and whenever we make conceptual progress on learning principles, we will make very huge practical progress very rapidly.
Well, let me see if I understand what you mean by that. So are you saying that there hasn't been sufficient progress in unsupervised learning? I'm thinking about the Google Brain work to date and others, some who think this is what we're going to continue working on.
So unsupervised learning, so if you look at applications, the overwhelming majority of applications rely entirely on supervised learning. For example, image recognition, speech recognition, machine translation. Every big success story, almost every big success story.
You mean useful stuff?
That's right. So unsupervised learning.
Key point.
No, but eventually the reason we do these things is because we want them to be useful. If they're useless, then we failed. So we will eventually come up with unsupervised learning algorithms which will outperform every supervised learning algorithm, but we haven't built them yet.
Right, and I wonder, I mean, as a follow-on, is it because you need something just like a human brain without all the rest? Isn't that interesting? Like, is there sort of critical mass where that methodology just doesn't really provide anything useful until it's actually smart?
Well,
by analogy, so not literally like an AI, but like if you were, let's say you were at a path to AI, that might you not get to a very interesting place until you've gotten to a very powerful place?
Oh yeah, we are at a very interesting place even today, and it will keep on getting more and more interesting. And right now we lack ideas. We don't know how to come up with these learning principles, but we will eventually figure it out. And once we do, you will see yet another explosion of applications. And with each serious advance in learning principles, we'll see very new and unexpected, unprecedented applications.
And then lastly, because this could be a segue to I mean, on a counter or agreement, do you think, were you saying that that's more powerful in your mind than advances in computational architectures themselves and the representational power of the nodes and fan out?
So by computational architectures, you mean the neural networks. So we will need, I think we will definitely need advances in both, but at least in my opinion, I think there is a relatively moderately clear path of how to advance the neural network architecture. And the way to advance it is the following. If you think about what a neural network does compared to previous machine learning methods, is that neural networks can learn a little bit of computation. You got those 10, 20 layer neural nets. You actually have a number of steps. You take your data, you break it into pieces, you combine it, you do some operations on it. If you imagine doing this for, let's say, 10,000 steps, then all of a sudden you can run algorithms inside your neural net. So if you can learn, let's say, some extremely deep systems, then now you can basically do anything a computer can, and there is nothing beyond that. So that's how I think progress in the neural network side, the kind of the model side of things will go forward.
Lastly, I mean,
yeah, to extend, answer the two questions about this going off into an alien intelligence. Basically, what works, right? We do what works. It's market driven, right? What works is what you can solve a real problem with. So I don't think these things are going to go off into the weeds and be some sort of alien intelligence, because it's always drawn back to what we as humans want, right? That's kind of what's driving development of these sort of algorithms and paradigms. And going back to the question of whether these things are going to continue to look more brain-like, I think it is interesting that we see these simple cell kind of emergent behaviors and things like that in these networks. But honestly, after having studied the brain, I think a lot of that is somewhat coincidental. There is so much complexity there. Some of that complexity may be useless in terms of computation, but the substrate on which we're building these computations is so vastly different, right? Silicon has so many different properties than the mush in your head, right? It's just the amount of signal leakage and all these kinds of things are so vastly different. I think it's actually going to look quite different. However, the behavioral constraints are always going to be this market-driven thing that us humans want to build something that we want to use or want to interact with. So at the behavioral level, yes, I think it's going to start looking very biological, very human, maybe first dog-like or something, but it's driven that way because we constrain it that way.
You guys are building silicon? I thought you were building mush for the head.
That would be great if we could do that, but we have a substrate that works, and we can do some very amazing things that biology can't do. Right? We can propagate a signal with almost zero loss. Right? Biology can't do that very well, and that set of parameters, a hyperparameter space, is very different for the brain than it is for a piece of silicon. A piece of silicon, we kind of design it in the synchronous fashion, so we have clocks and these kind of things. The brain maybe doesn't really have such constraints. not designed in the same way. So that's why I think like the underlying structure is going to start looking different. And that is one thing that's very exciting about deep learning is that using the computational paradigms we've come up with from an engineering standpoint, we're able to do something that sort of looks human-like, right? So that's a huge breakthrough. In my mind, that's just enormous, right? The ability to do that on this completely different substrate. So
yeah, I think it's fascinating. And that's right. I think it'll go just fine until it becomes self-aware. So I have a series of questions here from the audience, and I was trying to bucket and pattern match and do all that kind of neural network stuff on it. And there appear to be 4 that are all pointing in a similar direction, and it'll lead me to start with Adam, so I'll give you the heads up. The uber question seems to be, where's the money in deep learning, short and long term? Sort of like, show me the money. Like, what are the commercial obligations? One of the subpoints, which we'll start in a moment with you, which is, how does Clarify make money? We'll start with that one. The other related ones that others may or may not be interested in picking up are, someone asked, what are some of the consumer-based problems that deep learning could be commercialized to solve? So consumer apps, it seems like there's some immediately that you could speak to. And then another slightly more detailed question is, how about using deep learning for time series data, and are there applications in finance for time series data? But maybe first, the simplest one, how do you guys make money?
Is this a business school or something?
Well, I forgot, where are we here?
The best way to answer this question, I think, is to just maybe ask people to imagine the familiar. What's the most familiar business to you that you know about, or a product that you use on the web? I think that another way to do it is kind of like think about the things that you do on the internet. You buy things. You take pictures with phones. You look up things in search engines. So on one sense, images are just becoming more and more prevalent in everything we do. And again, I kind of like to talk about this as kind of like getting more about the physical world, the world we live in, into the world of computation. But so to cut to the chase, at Clarify, we're approaching it from several angles. The main thing is that we're looking for right now the low-hanging fruit, where the technology that we already have today, the things I showed, where is this just going to fit best into people's businesses? And there's all kinds of like little niche things that you wouldn't really have thought of before, and there's people emailing us that want to build smart refrigerators that know when the milk is empty and things like that. But we really we're doing a lot of work, and we're honing in on like common use cases.
Well, I would think, and you mentioned the commerce case, but I don't know if everyone realizes maybe what you mean by that would be, in any purchasing context, you're on Amazon, you're somewhere, you see a pair of shoes, but they're not quite right. Find me shoes like this. Find me whatever, flowers like this if you want to buy a bouquet.
Visual
like
search
there's
for
something pretty, but I don't quite know what that is because I'm a guy, right? And I want to get some of those, right?
There's a lot of interest, and there's a few companies that are doing this now, not necessarily with this technology. A lot of people are using Mechanical Turk type of things. But yeah, visual search for shopping. I see somebody on the street, I really want that jacket, and you take a picture of it, and find me the things out there, that specific jacket or things that are like it. And so that's kind of getting in the realm of things that we can do. And then of course, organizing your own personal photos. I think this is a pain point for a lot of people, and there's opportunities around that in the consumer space. And then there's a lot of B2B niches where we can help people with business. A lot of people businesses are paying money to humans to label data right now, to label images.
That's right.
And we can help with that.
I was thinking one of the killer apps for Google Glass would be to overlay all that sort of auto tagging of like, who's the face that you see in Facebook today. And so whenever you're in a location, you like Google beer goggles. So it could be like, who is that? And what's their name again? And look up the social, tag cloud of, are they creepy or not, or farm it out to hot or not, and get a quick judgment call on whatever it is you might have in mind. So anyone else want to take killer apps, either consumer or finance? Yep.
I love this question. How do you make money from deep learning? Well, you transform data into action. So, when we look at our customer base, which, spans 10 verticals, we see deep learning applied to everything from understanding your customers, understanding your market, to enabling people to be suggested or to purchase products, all the way down to, should I trade a stock or close my borders because of some illness maybe that might transfer into my country. So ultimately, it's already here. Who in the room has one of these? Cell phone. So if you have an Android phone, if you have a iPhone, you're already using deep learning. It transcribes your speech to some degree of accuracy, depending on system that you're using. But deep learning is already incorporated behind the scenes in so many applications that all of us use every day. We're seeing hundreds of millions of people touched through our customers every day, ranging from if you're on a news site, if you're buying a product, all of these things can be impacted. So I think there's a huge potential to make money. You just have to transform data into action.
Great. Did Google have any idea of consumer apps for?
So I can comment on it. I'm not sure. So I think that there are the basic applications of speech recognition and machine translation, I think, are really extremely important. Because right now, so for example, speech recognition, it's useful enough that I use it, and it makes mistake, and it frustrates me. And I would like to, for example, never to press any button on my phone again. I don't like that. And speech recognition could really make it possible for us to interact with the phone without using screens anymore. I think that'd be great. Machine translation, I think, is going to be very important, especially in the future. I think there are many countries in the world where people don't speak English, and it will be very important to be able to interact with people that live there. And if you have very good machine translation, very good speech recognition, then that alone, just those two things, I think they will have a very large impact.
I think a fundamental thing is you have to make somebody want something. That's the fundamental transaction that has to happen to make money on something, right? And driving user experience, that's really what it comes down to, right? Can you make a more rich user experience in the end? I mean, companies like Apple, this is what they do. And deep learning, machine learning is going to do that. We want our devices to become personalized, right? I mean, I think a killer app for me would be, I want my phone to be able to understand me better. I want it to learn and personalize its language model on my voice. It should be able to pick out my voice in a noisy room, or my friend's voice that it hears all the time, or it should be able to understand context. This is all driving my user experience. All the things that Ilya was just describing, they drive user experience. So it basically gets down to the point where it makes something cool enough that we want to buy it, right? Or in some way adds to our life. So
yeah, I think that's also the path that I can see towards an AI future that feels like step by step, like through a smart calendaring assistant that knows when you say I've got to get to the VLab event at Stanford, oh yeah, you're always late by this amount, so you better get going now, and did you do your slides? And before you know it, you have something that feels like your executive assistant.
Exactly.
If you used to have or do have such a person, and that when we get used to that, then it adds more and more, because what these techniques allow you to do is find these patterns that you don't even see yourself, but once they're pointed out to you, it's almost uncanny. I think everyone in the science of this at some point in their careers have had those sort of jaw-dropping moments, and maybe for different things. Maybe for some it was the image component that was similar. For others, it's just the sheer applicability of technologies across every different domain, as we just heard from Ilya. So one last question that maybe hopefully is relevant to a lot of the folks in the audience that was just recently suggested, which is maybe we can end with each of you giving us your advice with entrepreneurs and engineers in mind. In other words, what would you recommend they should do to enter this domain? Let's assume they aren't here because they're experts in it, but they're really curious. They've heard it's important. Maybe you've persuaded them it is. Maybe they're one of the folks who wish they were taking that class that's oh so popular and want to know what all the buzz is about. What would you recommend?
So if you're not an expert.
Let's say, somebody who's, maybe they're in computer science, but they just haven't thought about this field yet. Or they're not even computer science, and they're wondering, maybe, are there opportunities in data collection and processing? Are there ancillary things that this relates to? Or if they just want to be like you, what would you recommend?
I think if this is a pretty complicated field where details matter a lot, and so if somebody wants to enter the field, they should do as much as they can to become an expert. Even, I mean, if you run a company, let's say, you should be more of an expert than the heads of the competing companies.
But I thought you said it was easy.
Well, it's easy. It's easy in the same way that rocket science is easy. It's really easy. It's really easy to understand why a rocket goes to space. It has a lot of fuel. It burns the fuel goes down. Then the first stage detaches. The second, easy. What's hard is rocket engineering. Building a rocket, and you want to go to a faraway planet, you just build a really big rocket, but you need to make sure that the materials are going to work and that nothing will break down and that you won't have corrosion. I don't know what issues are there. I think that's the analogy. The principles are easy to understand. Actually making it work is hard. But I think it's obviously important to know as much as possible for anyone that wants to deal with this stuff.
I can tell you what you don't want to do. You don't want to design processors for 12 years and then get a PhD in neuroscience. That's kind of a long way to go. But one thing I think that's very important is understanding the capabilities. I mean, getting down to the nuts and bolts, that is obviously very important, and that's the engineering side of things. But from sort of the product design side of things, you need to understand what can be done, right? What are the capabilities? What are the limits? And then you can really start thinking, how do I chisel out a use case, right? And that doesn't require all of that engineering expertise, I don't think. I mean, you need to have some sense of it, right? But that's really, I think, very fundamental right now, because we're getting to the point where that engineering is starting to get democratized, right? Hopefully, in the next 5 years, I think that's going to start happening. And then it's like, well, how can we really use this and apply it?
Go ahead, Adam. Yeah.
Well, I think it's actually quite easy to play around with this stuff these days. That's one of the cool things about, well, computer science in general. You just need a computer. You don't need a factory or a rocket. There's Kaggle competitions and a lot of data sets that are out there online, and a lot of this work is public, and very, very, state-of-the-art stuff is open source, and it's actually quite easy. You have to have a background in computer science, or not really, you just have to know how to program. So that's step one. If you're not there, learn how to program. But I think it's quite, we talked a lot about just like massive amounts of data and GPUs and all this stuff, but like you can make progress and definitely make progress in terms of understanding with playing around with stuff at a small scale, and that's how you become an expert.
I would agree. We're seeing now in open source small toolkits become available where if you're wanting to play around with this stuff in a small scale, if you're interested in the science behind it, you can do it, right? There's papers to read. Ultimately, if you're trying to apply it to business, my perspective is probably a little different than many in that, I believe that you should focus on creating business value. Find a real business problem to solve, then look at the capabilities, as he said, and see if deep learning can apply to your problem. But don't be searching for some problem that you can apply deep learning to. That's a solution looking for a problem. Ultimately, find a problem to solve that's meaningful, that people want, and see if deep learning applies to that. It's just another tool in our tool belt. That's it.
Interesting. Yeah, I don't know, I was thinking about that question myself since it came from the audience. There's something about being inspired by biology that, at least for me and the folks I knew, seemed to spark a curiosity in this sector. Well, actually, maybe I should ask, because I got the sense it did for you. I'm not sure really if it was or not, this notion that there's something biomimicry-like here that seems very powerful. Or was there some other locus? Like, why did you end up here? Maybe it's a different way to count this, of all things that you could have been working on. Like, how did you choose your advisor when you were doing your PhD?
Well, I mean, being the analogy to biological systems was one of several factors. The thing that I liked the most were two things. I felt that so obviously, artificial intelligence is important, so I wanted to work on that. But with neural networks specifically, they seemed powerful. And they had a very nice feature that after you train it, it produces something that you may not necessarily understand. And that seemed very satisfying because you are solving this very incomprehensible problem. You sprinkle it with a simple principle, and you get an incomprehensible solution. And that seems very neat.
Yeah, sort of maybe to wrap up, I'm reminded of comments that Bill Gates, Larry Ellison, Nathan Myhrvold, and I think Charles Simonyi all said is that if they were back in school today, they would be studying biology or biological engineering. I think they were speaking primarily out of their fascination with the compact representation of genetic code and the interpreters in our ribosomes that build our bodies and the world around us, how incredibly powerful they are as information systems. And I think in the genomics and healthcare world, you have this revolution that's going on that's shedding more and more light about how biological information systems work. It's cross-pollinating with the computer science field in all kinds of interesting ways. This is probably the most powerfully exploited way that feels like a computer science thing. But the back and forth is profound, right? There are people at other parts of Stanford building information registers in cells, building logic gates within the DNA of organisms that I think will enter into a brave new world where this information sharing and sort of inspiration goes both ways. And maybe to end with one last quote, I'm reminded of Arthur Clarke, who said, any sufficiently advanced technology is indistinguishable from magic. And so I'll just remind you once again, everything that you see kind of feels magical in the CS department over the next few years probably is going to relate to something in this domain. And it certainly seems advanced to me. So thank you very much to all of you for coming here today.